Okay, so welcome back to this next video in which we are discussing angiogenesis and angiotherapy. Okay, so we've now discussed the angiogenesis pathway induced by an area of hypoxic tissue. Okay, what we now want to talk about is angiotherapy, which is where you target the angiogenesis pathways, either promoting them or blocking them for therapeutic purposes. And the three examples that we're going to look at are angiotherapy for cancer, which is a real thing now. This is used clinically. Okay, there is one drug which targets angiogenesis and blocks it. We're also going to look at angiotherapy for retinopathy as a result of diabetes mellitus. Okay, and again, it's the same drug, bevacizumab, trade name Avastin, which is used to block angiogenesis there. Okay, and then we're going to look at something which isn't yet a clinical reality, but which is a hope for angiotherapy in the future, which is coronary heart disease, where you would want to have the opposite effect. You'd want to have a pro-angiogenic effect. You'd want more angiogenesis, basically. Okay, right. So we're going to start off by discussing angiotherapy for cancer. Okay, so cancer. So I'm just going to do a brief summary of how cancer develops, okay, and how it actually kills you in the end. And then we'll look at the importance of angiogenesis in cancer, okay, and then we'll look at the drug which blocks angiogenesis and which is now used to treat cancer. And then we'll talk about why this drug isn't particularly effective, okay, potential reasons for why it isn't particularly effective. After all, they are only hypothesis. Okay, we don't know why the drug isn't as effective as we hoped it would be. Okay, right. So let's go over the carcinogenesis process then. So the leading theory of how cancer develops is that you start off with a normal cell, which is generally an epithelial type cell. Okay, cancer usually develops in epithelial cells. So, for instance, cells of the skin are epithelial cells, cells that line the gastrointestinal tract are epithelial cells, cells that line the liver, the pancreas, the urogenital tract, the lungs. These are all epithelial tissues. Okay, so they're the main places in which cancer arise. So what you do is you start off with a normal cell. Okay, so here is our normal cell, and then the idea is that this normal cell gets a mutation, okay, and because this mutation is occurring in a somatic cell rather than in a cell that's going to lead to the development of the entire body, okay, it's called a somatic mutation. Okay, so it's a mutation that only occurs in a single cell of your body, rather than a mutation that's in one of the cells that is going to make your entire body, for instance, okay, which will be called a germline mutation. So if you've had a mutation from development and your entire body is full of cells with that same mutation, that's called a germline mutation. Okay, a somatic mutation is a mutation that occurs in a single somatic cell. Okay, so you get a somatic mutation in some somatic cell, and this somatic mutation is going to allow this cell to over-proliferate, basically. Okay, it's thought that the first mutation that occurs in the carcinogenesis process is a mutation that allows the cell to over-proliferate. Now, there's two ways that you can do this, okay, because the control of whether a cell is going to divide or not is a balance basically between two forces. Okay, there are proteins which are pro-division, okay, and these are called proto-oncoproteins, okay, or proto-oncogenes is the name for the gene which actually encodes the protein, so called proto-oncogenes. Okay, so proto-oncogenes code for proteins called proto-oncoproteins, and these proteins are pro-growth. Okay, they try to make the cell grow and then split into divide. Okay, whereas the opposite force is what's known as tumor suppressor genes, which code for tumor suppressor proteins, and these proteins have the opposite effect. They try to inhibit growth and proliferation. Okay, and I'm sorry, I've just put tumor suppressor proteins rather than tumor suppressor genes. That's a little bit inconsistent, so I'll cross out the proteins and then put genes there. Okay, so that it's consistent between the two. Okay, so Basically, normally, in a cell that is not dividing, you have a balance between the activity of the proto-oncogenes, which are driving forward division, and the activity of the tumour suppressor genes, which are saying, halt it, stop it, put a brake on that, okay? And the cell, therefore, does not divide. However, if you either promote the proto-oncogenes, so you bump up the activity of proto-oncogenes, or if you dip down the activity of the tumour suppressor genes, you can tip the balance in favour of division. Okay, so there are two different ways that you can tip a cell into dividing, either bumping up the activity of the proto-oncogenes or damping down the activity of the tumour suppressor genes. Okay, so this somatic cell, its first mutation is going to either be a mutation that increases an activity in the proto-oncogenes, okay, so some gain of function mutation in the proto-oncogene, and for short, a gain of function mutation is abbreviated GOF, gain of function. Okay, so either you're going to get a gain of function mutation in a proto-oncogene that's going to mean that the proto-oncogene activity goes up. Okay, so for instance, you could imagine a amplification mutation for a certain proto-oncogene, which results in you having too many copies of the gene for that proto-oncoprotein, and therefore you end up producing much more of the proto-oncoprotein, and that causes the cell to over-divide. Okay, alternatively, you can have a loss of function mutation in the tumour suppressor gene, okay, where it now loses activity basically, and that would also tip the balance in favour of the cell dividing. Okay, so here is this cell in red. It's now undergone a mutation, and this is now going to lead it to over-divide. Okay, so the cell will now over-divide and produce a whole clone of cells that are all identical to it and which all have the same mutation that allows them to over-divide. So you've now gone from having just one cell with this mutation to having loads of cells with this same mutation, and you see how this spreads now, okay? By virtue of what the mutation is, it means that the mutation effectively spreads, okay? Other mutations, it would just stick with a single cell basically. You'd have a single cell with this mutation, but it wouldn't be that much of a problem. Whereas these mutations, because of what they are, they amplify themselves because they cause the cell to over-divide, and then you make loads of cells with this same mutation, so you end up with a clone of cells that are all capable of over-dividing. Now, this is absolutely not cancer yet. At the moment, this is only suffered one mutation. This clone of cells only has this one mutation. You need to get a lot more mutations if you're going to become cancerous, and that's the basic theory for how cancer develops, that in order to turn a normal cell into a cancerous cell, you need absolutely loads of mutations. You need to collect up mutations that give the cell an abnormal enough phenotype that it is then cancerous, basically. And the mutations that you need in order to turn a normal cell into a cancerous cell are not set in stone, basically. There are loads of different combinations of mutations in different genes which will do, basically, and will give you this cancerous phenotype. So cancer is not just one disease, it's not just one set of mutations that you need to acquire. There's loads of different sets of mutations that you could acquire which would turn a normal cell into a cancerous cell. Cancer is defined by the phenotype, not the genotype. Okay, right. So if this lump of cells that we have here was visible, then we would call it a benign tumour. If it wasn't visible, then we wouldn't even be able to diagnose it, and therefore we wouldn't call it a benign tumour. Okay, but you can call it a benign tumour if you want. At the moment, it's not cancerous. These cells are not aggressive enough to be considered cancer. Okay, they haven't got enough of the phenotypes that characterise cancer at the moment. Okay, so what now happens is a gradual evolutionary process of the tumour. Okay, so here's the beginning of our tumour, so I'll put that key word there. And now what's going to happen is a gradual evolutionary process, and it's often called a micro-evolutionary process because it's going to occur over a short time scale, basically. And what I mean by this is that the population of cells in this tumour are going to evolve, basically. They're going to change over time. At the moment, the tumour consists of entirely red cells, this clone of cells that has this single mutation that means that it overproliferates. Over time, the dominant clone of cells in this tumour is going to change. Now, let me explain how this is going to occur. So basically, you can wait for a certain amount of time for one of these cells to undergo a mutation that is now going to give it another phenotype towards being cancerous. Overproliferating was one of the phenotypes of being cancerous. Okay, we're now going to wait a certain amount of time for another cell to get another mutation that's going to take it closer to the cancerous phenotype, another mutation that's part of this combination of mutations that it needs to acquire in order to have a cancerous phenotype. Okay, and this, we don't know how long it will take. It will vary, basically. Okay, in this population of red cells, cells will be undergoing mutations all the time, basically. Most of these mutations will get repaired. The ones that remain, some of them will be fatal to the cell, okay? Eventually, if you wait long enough, one of them will get a mutation that takes it further along the way to cancer. Okay, so maybe it gets a mutation in another proto-oncogene or another tumour suppressor gene that allows it now to overproliferate even more. Okay, so if I draw what's now going to happen, let's say this turquoise cell here is going to get another mutation in another proto-oncogene or another tumour suppressor gene that makes its proliferation even faster than the red clone of cells. Okay, so it's now going to take over that tumour, basically. The red cells are going to look fairly sparse now compared to these turquoise cells, and the tumour will get bigger and bigger and bigger and bigger. Okay, like so. So now the dominant clone in the tumour is now these turquoise cells. So the tumour population has evolved. It's gone from being a population dominated by red cells to being a population dominated by these turquoise cells, which have got 2 mutations now. Rather than just 1 mutation, they've now got 2 mutations. Okay? 2 mutations in proto-oncogenes or tumour suppressor genes that now mean that they're capable of overproliferating even more than the red cells. Okay, so they're going to come to dominate the tumour, and that's what I mean by the tumour population evolving. Basically, it's gone from being a population of entirely red cells to now being mainly a population of turquoise cells. Okay, right, and it really is a survival of the fittest process. Okay, the turquoise cells are better equipped to survive because they divide more quickly than the red cells, and therefore they come to dominate the population. Okay, it's simple as that. Right, now what's going to continue happening is you're going to continue evolving the clone of cells, basically, by this accumulation of mutations. And what I mean by this is in this turquoise population of cells, the new dominant clone in the population, we just now have to wait for one of these cells to get a further mutation that takes it further along the way to cancer, okay? And generally that mutation will now give it a better ability to survive over the turquoise cells, and therefore it will now come to dominate the population, and then the tumour will have evolved even more, and every time it evolves, gets a further one of these mutations, the tumour will generally be getting bigger because the cells that in that clone will be now getting closer and closer to cancer, more and more aggressive, basically. Okay, and over years and years potentially, this process will be continuing, and you'll be gradually building up a more and more aggressive clone of cells as the dominant clone of cells in the tumour. Okay, and let me outline now some of the properties that these cells are going to be gradually accumulating through this gradual accumulation of mutations. Okay, so obviously the key one is that they're going to be capable of overproliferation. Okay, they're going to completely overdivide. Okay, but in addition to overproliferation, there are other important ones. So for instance, often by the time they get to cancer, what they have acquired is genetic instability. Okay, and this is quite an important concept. This is thought to be one of the mutations that occurs early on in the carcinogenesis process. So what does genetic instability mean? Well, genetic instability means that the cells undergo mutations faster. Okay, now how does this occur? Well, basically cells get their DNA damaged all the time, okay, and the reason that it doesn't cause a mutation usually is because of DNA repair mechanisms. Cells have very good DNA repair mechanisms for fixing problems with DNA, okay, and this prevents the change being permanent, basically, i.e. it prevents a mutation, okay. If you got a mutation that meant that DNA repair mechanisms were now broken, basically, or a certain DNA repair mechanism no longer worked, okay, then that would mean that when your DNA got damaged in the way that would normally be repaired by that certain mechanism, it would no longer be fixed, and therefore you would accumulate mutations much more rapidly. Okay, so that's how you can acquire genetic instability. Now, why in the end clone of cells, which we will call cancer, do you generally find genetic instability? Well, it's thought that the reason for this is that genetic instability is crucial in propelling you forward in the process of developing cancer. Okay, so I've discussed that for a normal cell to become a cancerous cell, you need to have this accumulation of a combination of mutations. So you need to get, it's thought generally around 7 or 8 mutations to turn a normal cell into a cancerous cell. Okay, and this is a long process. Waiting for cells to undergo mutations that are permanent is a long process. It would incredibly speed it up if we had a clone of cells that was genetically unstable. Okay, so imagine that the next mutation in this turquoise clone is going to be something that causes genetic instability. Okay, let me show you this now. So let's say one of these cells in this turquoise clone, let's say this blue cell here, let's say it gets a mutation in some DNA repair mechanism, and I've just realised blue isn't going to show up at all against turquoise, not in this slide anyway, so I'll colour it in purple there. Okay, so let's say this purple cell gets some mutation in a DNA repair mechanism that now means that it is going to be genetically unstable. Okay, now because it's already got the mutations of the turquoise cells, okay, those 2 mutations that lead to it completely over-proliferating, it will now over-proliferate and produce a population of unstable cells, genetically unstable cells within our tumour. Okay, so if I draw the tumour now, here we go. So this mutation won't cause it to over-proliferate initially, but it's already got the over-proliferation mutations that the turquoise cell had. So the point of that is that now you're going to end up with a whole population of cells that are genetically unstable. And yes, this mutation won't lead to this clone of cells dominating over the other clones yet. But now what it's going to mean is that this new clone of cells that we've got here, the purple cells, these are going to progress along the process much more quickly, because now the frequency of mutations in that purple clone is going to be much greater than it is in the turquoise clone. Okay, so now in this purple population of cells, much more quickly than in the turquoise clone of cells, are you going to get another mutation that then allows you to over-proliferate even more. And then when you've got that mutation, then you will come to dominate the entire tumour. Okay, so that's why genetic instability is thought to be a really crucial acquisition at some point in this carcinogenic process, because without it, it's thought that it would take too long to actually acquire 7 mutations and go through this gradual process, because mutations are so rare is the reality. Okay, so that's why genetic instability is thought to be really important. It accelerates the process now. After you've got this genetic instability mutation, the subsequent steps in this process can now go much more quickly, basically. You're going to acquire the next mutations and create new clones much more rapidly, and the evolution of this tumour is going to occur much more rapidly. Okay, so that's one of the key things that you find finally in the cancerous cells, because it was one of the key things for the development of the cancer cells, basically. Okay, to actually get cancerous cells arising in a human lifetime, it was necessary at some point to get a mutation that led to genetic instability to accelerate the process along. Okay, right, other things that you find are lost senescence. Okay, so what does this mean? So basically, cells in the human body which are capable of dividing, okay, and not all cells in the adult human body are capable of dividing. So for instance, myocytes, both skeletal myocytes and cardiomyocytes, are not capable of dividing. Neurons in the brain and the peripheral nervous system are not capable of dividing as a hard and fast rule. It's not quite true. In the hippocampus we are starting to find division of neurons, okay, but it's nearly true that neurons don't divide, okay, but the cells that do divide in the adult humans, such as skeletal muscle cells, hepatocytes, fibroblasts, basically, if you take one of those cells out and put it in a lovely petri dish, okay, so here we have a lovely petri dish full of growth medium, okay, and give it all the signals it needs to grow, okay, the cell will not divide forever. Okay, you can't get it to divide an infinite number of times, basically. Okay, instead, what happens is the cell will divide a certain number of times, and then after that, its progeny just will not divide again. So here is our cell that we've taken out of the body. That's a fibroblast, and we now get it to divide, and it will divide and divide and divide, but it will only go through a certain number of rounds of division, and then when you finally got to that final generation of cells, those cells will not divide again. Okay, and the reason is that the telomeres at the end of the chromosomes get shorter every time you divide, basically. Okay, so with this division, these two daughter cells here have shorter telomeres than this cell here. Okay, and then the next generation after that will have shorter telomeres than this generation previously. Okay, and it will continue on until you finally get to the point where the telomeres are all gone, basically. And if you continue on dividing your DNA, you'll start instead cutting bits off the actual chromosomes. Okay, cutting bits off the genes rather than the telomeres each time you divide. Okay, so you can't go on, basically. Okay, and that's called senescence, that property that eventually you will stop dividing, even if you have enough resources to continue dividing. You will not divide infinitely. You will go into senescence eventually, okay, where you stop dividing. Okay, it's also the concept of a Hayflick limit, that there is a limit to how many times you can divide. Okay, obviously tumour cells have to somehow get round this, otherwise they're eventually going to get to the point where they can't divide anymore. Okay, and the way that they generally get around it is by getting some sort of mutation that results in an overactivation, an expression of an enzyme called telomerase, okay, which is capable of extending the telomeres back up, and therefore you can divide as many times as you want because this enzyme can just keep extending your telomeres back up. Okay, and then you will never hit senescence. Okay, so that's one of the key things that needs to be acquired at some point in this evolutionary process. Okay, the other one that I'll mention is lost sensitivity to apoptosis, so invulnerability to apoptosis. So again, another property of cells which are dividing in the adult human body, so for instance hepatocytes, fibroblasts, smooth muscle cells, is that if the cells in those tissues become too overcrowded, then the cells will apoptose. Okay, so let me show this. If the cells become too overcrowded, then what will happen in normal tissue homeostasis is that you'll start to get cells dying, basically. They'll commit apoptosis to depopulate and give more space for the other cells. Okay, that's a process called apoptosis, programmed cell death. Okay, so that's normal tissue homeostasis, that if the tissue becomes overcrowded because the cells have overdivided a little bit, they'll start apoptosing. Tumours are incredibly overcrowded, okay, and if the tumour is going to actually get to a certain size, then obviously apoptosis needs to be overcome at some point. So one of the mutations that will occur in this evolutionary process is some invulnerability to apoptosis, so that the cells do not commit apoptosis because of overcrowding. Okay, so those are some of the key mutations that are going to occur along this evolutionary process. They're not all of them. Okay, so I've missed out the final mutation in this list, okay, the final key mutation, okay, which takes you from just having a massive, great benign tumour to actually having cancer. Okay, so let's say you've gone through this evolutionary process, the clones have been evolving, the dominant clone has been changing, and it's gradually been acquiring more and more of these phenotypes here. Okay, and we've now got a clone of cells that is dominant in our tumour that has all of these phenotypes. It is not yet cancerous. There is one last hurdle it has to get over in order to actually become cancerous, which is believed to be the final thing that occurs in the process towards developing cancer. Okay, and this final mutation is something that leads to motility, basically. Okay, so normal cells in the body are not motile. Okay, the tip cells were very, very special in that they could move. Okay, normal cells cannot move around in the body. Okay, the key property that cancerous cells are going to acquire is that they're going to be able to suddenly start moving around in the body. Okay, the benign tumour that you've got at the moment was static. It was not invading the surrounding tissue, and it was certainly not casting off cells into the bloodstream to go and invade far off tissues. Okay, the transition from a benign tumour to a malignant tumour, which is cancer basically, is that the cells are suddenly going to gain motility, and they're going to gain the ability to invade the surrounding tissue and go into the bloodstream and then invade far off tissues. Okay, so a malignant tumour is cancer. Okay, and the thing that's going to happen is that they're going to gain the ability to move. So the final mutation that's going to occur is that they're going to, in this final clone of cells, and I know this was only the third clone of cells here, I think, but let's say this represents the 7th or 8th clone of cells. The final mutation that is going to occur is that the cells are going to gain the ability to be motile. Okay, so I'll just draw my benign tumour here, and in the clone of cells what you're going to get is one cell that just so happens to gain the ability to be motile. Then of course it's going to be amplified because the cells over-proliferate. Okay, they've got that mutation long ago in this clonal evolution process. So you're going to end up with loads of these cells with the ability to move. Okay, now, generally the way that these cells acquire the ability to move is that they turn back on a program for moving that was available in development, basically, in embryology. Okay, which isn't usually used in the adult at all. So you remember I told you that most tumours arise from epithelial cells. Okay, now in the embryo, epithelial cells cannot move. Okay, and in order to move, which occasionally needs to happen in embryology, what has to happen is the epithelial cells have to change into mesenchymal cells. So let's have an epithelial cell represented here. Basically, if it wants to move, it has to undergo a process known as EMT, okay, and turn into a mesenchymal cell, which I'll show here. Okay, so this represents our epithelial cell here. Okay, epithelial cell, and this down here represents our mesenchymal cell. And basically, this is a process that can be used in embryology. If an epithelial cell wants to move somewhere else, it firstly becomes a mesenchymal cell by this process known as EMT, which stands for epithelial mesenchymal transition. So the E is for epithelial, the M is for mesenchymal, and then the T is for transition. Okay, then the mesenchymal cell can migrate, basically. It can use filopodia to move around like the tip cell. Okay, and then once the mesenchymal cell has got to its new location, what can then happen is it can convert back to being an epithelial cell for a process known as mesenchymal epithelial transition, MET. Okay, so the idea is that usually the way that this final clone of cancer cells gains the ability to move is it turns back on this process of EMT that was used in embryology, used in development, but what is not used in the adult, it's turned off. Okay, so they gain the ability to do this embryonic behavior, basically. Okay, so what this now means is that these cells here in this tumour can now undergo the epithelial mesenchymal transition. They can then start moving out of the tumour into the surrounding tissue. Then they can undergo the mesenchymal epithelial transition, return back to the epithelial cell, and then they can start dividing over there, and they can set up another little tumour further away from the original benign tumour in the surrounding tissue. Okay, so they start invading whichever tissue they're in. So for instance, if it was in the liver, you're now going to start getting the benign tumour spreading out from where it originally was into the surrounding liver tissue. Okay, so this is the property of invasion, basically. So this motility mutation allows it to invade. Okay, it becomes invasive. Okay, the other scary thing is that now what can happen is some of these cells can undergo the epithelial mesenchymal transition. They can move, and then they can end up going into blood vessels. So let's say this is a blood vessel here. Okay, and then the mesenchymal cell is now in the blood, and then it can leave the blood in some far off distant site, let's say the brain here, okay, and then it can undergo the mesenchymal epithelial transition back to an epithelial cell, and then of course it can set up another tumour in the brain, which is not a primary tumour but a secondary tumour. Okay, so you can start getting it dividing in the brain. Okay, and this will be called a secondary tumour at this far off distant site. Okay, and there's another name that people use for secondary tumours, which are to call them metastases. Okay, and the process of a primary tumour sending off metastases in other tissues is known as metastasis. Okay, so these are the two key properties that this motility mutation gives the cells. It allows them to become invasive and metastatic, basically. And usually the way that cancer kills you is that you get metastases in the brain, and that is what usually kills most cancer patients. Okay, right, so that's an overview of what occurs in cancer. Okay, now what we want to discuss is the importance of angiogenesis in cancer, and I did not put this in my list here, which is why I warned that this list was not complete of all of the phenotypes that cancerous cells have acquired by the time they finally become cancerous. Okay, and this is the final cancer cell here, this yellow cell here. Okay, once it's gained the motility mutation. Okay, but in this list you're also going to need the ability to sustain angiogenesis. So let me now talk about this. So basically it turns out that tumours cannot get to beyond the size of 1 to 2 millimeters without having angiogenesis, basically. Okay, so they can't get bigger than 1 or 2 millimeters. Now let me show 1 or 2 millimeters. That's about the size of 1 or 2 millimeters, that dot pretty much. Maybe a little bit bigger than that. That sort of size. Okay, so they can't get bigger than that sort of size without having angiogenesis occurring into them. Okay, now this is still a big controversial point. Okay, some people argue that once you form the tumour, the cells in that tumour will all become hypoxic, okay? And then what will happen is they will do the exact pathway that we have spent so much time going over. They'll start producing vascular endothelial growth factor, okay? This will start signalling to the local capillaries and getting them to form sprouts, which will converge on the tumour, and therefore the cancer cells the cells of the tumour surely don't need to acquire any sort of mutation to actually get the angiogenesis to occur. Surely it's just a normal physiological process. They can just hijack the normal physiology and they'll get a blood supply that way. However, it doesn't seem to be that way. Okay, for some reason the tumour cells don't seem to activate the physiological process. Instead, it seems that they actually need to acquire a mutation in order to activate the angiogenesis pathway, basically. Okay, so the evidence for this is that you can have tumours sitting for years and years and years at this sort of size, at 1 to 2 millimeters in diameter, which are not growing any further because they are not getting angiogenesis occurring to them, okay, even though they must be very, very hypoxic. So it is thought, the opinion is emerging that actually what needs to occur is at some point along the clonal evolution process towards cancer, one of the steps into the next clone needs to be some mutation that leads to the over-signaling of the angiogenesis pathway. Okay, so potentially some mutation that leads to the overexpression of vascular endothelial growth factor A, or something along those lines. Okay, so that you get massive angiogenesis signaling, and then you get a blood supply growing into the tumour, and then the tumour can grow beyond 1 to 2 millimeters in size. Okay, so that would be a massively advantageous move forward for the clone of cancer cells. Okay, so it is gradually starting to emerge as the general opinion that in order for you to develop into cancer, at some point you need to get a mutation that causes the overactivation of angiogenesis. So I might just add that onto this list. Now, I wouldn't really put this as number 1. Overproliferation should be number 1, but I can't put it anywhere else, so I'm putting it right at the top here. Okay, so some way of inducing angiogenesis, basically. And if you don't get that mutation that induces angiogenesis, you'll just stay at this tiny little size. Of course, the cells will still be dividing, but then they'll be dying because they're hypoxic, basically, so it just can't get bigger than that. Okay, so what's thought to happen is that the tumour will sit at this size for ages until one of the cells in the dominant clone gets a mutation that allows it to have over-the-top angiogenesis signaling. Okay, maybe an overexpression of vascular endothelial growth factor A, and then suddenly you'll start getting angiogenesis occurring into the tumour, and then the tumour can now grow much, much bigger now that it's got a new blood supply which is bringing in nutrients to it. Okay, and this concept that the tumour will sit at that size until one of the cells is lucky enough to get a mutation that overactivates angiogenesis, this is the concept of the angiogenic switch. Okay, so people call it the angiogenic switch. They say that the tumour turns on the angiogenic switch, basically, or the tumour is waiting to undergo the angiogenic switch, where suddenly a cell gets a mutation that overactivates angiogenesis, and that now will emerge as the dominant clone, and then the tumour can grow bigger and bigger and bigger. Okay, right. So this is why people turn to the idea that we should be trying to target this. We should be trying to stop angiogenesis. Okay, and if we stop angiogenesis, then the tumour will have to be stuck at the size of 1 to 2 millimeters. Okay, so this looks as though it could be a really hopeful cure for cancer, basically. Okay, and let me just give you the name of the person who first suggested that we could target angiogenesis for cancer. Okay, so Judah Folkman was the first person who came up with the idea that potentially a way of curing cancer would be to target angiogenesis and block angiogenesis, to block the development of this new blood supply to the tumour and keep the tumour at that small size. Okay, right, we'll call it there for this video. That's the motivation for using angiotherapy in cancer. In the next video, what we'll look at is the drug that we now have which can block angiogenesis in cancer, and we'll look at, unfortunately, the reality, which is that it only has a modest effect at improving cancer.